Uh, y'all have a nice weekend. I hung out with this kid all weekend, which was really nice. Yeah, my wife is now back to work, so it's a little bit more like like she's not at home to take care of her. So yeah, I get more time with her during the week, which is really super lovely. So this is a big one today. Where you'll remember the concepts we left off with the last time. So we spent some time walking through the basic ideas of the central limit theorem and sampling. We started part 3 with random variables. So random variables, essentially just our data is the realization of multiple draws of a random variable, what we call a sample. And so what we did in part 3.1, right after the mini exam last week, was talk about random variables as their own separate topic. We're going to come back to these. Random variables are not just important when we think about the underlying probability distribution, but once we turn to this idea of sampling, where we draw from an underlying random variable multiple times, in general, we do not observe what that underlying probability distribution looks like. So the data generating process for the random variable, for the sample. So what do we do when we don't know the underlying distribution? Real question for you. When we don't know the underlying distribution that generates the samples that we observe. So I'm asking, like, what are the wait times at a restaurant? You don't know what the wait times. You know what the wait times are, the ones that you've seen, but you do not know what the data generating process is, the random variable. You will never observe it. I don't know the ages of students in Econ 0150 classes. All I see is that I see your distribution of ages in this class, which is a draw from the underlying random variable. So what do we do in that case? Well, amazingly, we have the central limit theorem, which tells us when we take larger and larger samples, when the sample size grows, that the distribution of the sample mean, we take the average of everyone's ages as the sample grows larger. That follows a normal distribution, or it approaches a normal distribution, that's centered on the truth, and the distribution gets tighter and tighter around the truth as the sample size gets larger. This is one of the most amazing results we have. It allows us to do everything else that we are about to do in this class. This is the foundation. We spent all of last class simulating this with die rolls. So you'll remember the notebook that we played around with last class. So this was, I just had you calculate a bunch of, or basically roll a die, which gave me a number. So each of you, you'll remember this, each of you rolled a die on your computer, gave me a number, and then I collected a bunch of die rolls. So this is from, this commented out one is from your class, and then I calculated one from the class after you. And then we plotted the distribution. So we know the sample that we constructed. Each of you rolled a die, and I plotted this. And this, may look normal, like a uniform distribution, which it is. Like rolling a die is actually a uniform distribution, but it's not exactly a uniform distribution. So the first takeaway from last time is that we don't always, it's not easy to observe what the underlying distribution is simply by looking at the data. Often it looks a little bit noisy like this. So what we did is we actually increased the sample size, and as we increased the sample size, similar to the idea that there are many ways of getting a 7 when you roll 2 dice, the center point of the data, the sample mean, started collecting a peak. So we got this peak right in the middle of the distribution. So as we took the average of two die rolls, we got closer to the, most of the data sort of clustered around the middle. And you'll know that the average die roll is 3.5. So as we increased the sample size from 1 to 2, we got this clustering around the truth. And then as we increased the sample size even further, we not only got clustering around the truth, but we started developing this curvature in the distribution, where this, it's kind of peaked in the middle, but if we ran this a bunch of times, it would be sort of peaked, but then fall off linearly on both sides. As we start increasing the sample size, we get this curvature, and you can see that when we start talking about sample sizes 3 and larger. So here we can start seeing this curvature, which a lot of you recognized as a normal distribution, which we had talked about in the previous class. So as we continue to increase the sample size, we get peaks that concentrate in the middle and have this bell shape to them, which is the standard shape that we see with a normal distribution. And this is about where we left off last time. We said, look, we don't need to know the underlying distribution to be able to make claims about what the distribution of the sample means are. And that itself is phenomenal. What we're doing today is using this idea to then allow us to make claims about how close our sample mean is to the truth. And what we're going to do today is I'm going to give you the true sample mean for the running example for today. But we're just going to use this to make claims about how close the sample mean is to the true mean. But you're never going to be able to see the true mean. So this is just to show us. We're going to assume that we don't know it, even though we do. So we'll walk through it in this way. And I'm going to show you how we use this fact to then build up the core test of how close our sample mean is to the truth, on average. This is going to, how many of you know of the t-test? Probably everyone in this room has used a t-test before. This is where we're going. To correctly use a t-test, I think it's pretty important to be able to know what the t-test is doing. And every semester, I see lots of students coming in with experience running a t-test, but without the intuition for what it's actually doing. So over the next couple of class periods, over the next 2 class periods, we're going to be developing the intuition for the t-test. Okay, so this is where we're going. A bit of housekeeping, so homework 3.1 and 3.2 are posted. Those are due on Friday. And then as we get through parts 3.3 and 3.4, those will also be due on Friday. So I gave you a break last week, but this week we have a bunch of work to do. And then mini exam 3 is on Tuesday. So we're going to be about every other week for the rest of the semester with mini exams. So that'll be on Tuesday, a week from today. How many of you would be interested in a review session, like on a Sunday? Okay, raise your hands high. By raising your hands, you're like kind of committing to coming to it if I hold it. Look, I'm giving, to hold a review session now in my life, I have to give up precious time with my daughter. So maybe we'll do it for about an hour on a Sunday afternoon. It sounds like there's some interest. We'll see how this goes, and then maybe we'll hold review sessions the rest of the semester. I think we're starting to hit some of the more kind of theoretical concepts that might benefit from a review session. So now is about the time. Also, office hours for the undergraduate TAs, it's on the course page. So all you have to do is click over to the main page. And you can see Olga and Thomas have really nice office hours. Olga was in the class a year ago. So she's been through the sequence. It was a little bit different when she took it, but since then she's gone on and studied more with probability and statistics and done a lot with regression. So she's going to be a really good resource for you. The same with Thomas. He has a great background in statistics and coding. So they're both very knowledgeable, and I know it can be scary sometimes. So if you want someone who's also a student to go talk to, they are a great resource. So don't hesitate to drop by their office hours. Okay, so that's all, I think, the main housekeeping items. Any questions before we get in? Y'all doing great? It's a dreary time, but it's not raining inside, so I think we're good. So the main thing we're talking about today is how we measure closeness between the population, which we do not observe, and the sample. So we do observe the sample. How do we know how close it is to the truth on average? So that's the main question we're asking today. We know we never observe the population. I've already said this like 3 times. I repeat it over and over again. We do not observe the population. We do observe the random draws from the unknown random variable. How do we know how close what we're seeing is to the truth? So we're actually going to simulate this today. So I have a nice notebook that you can click on to actually generate some data, and we're going to check whether the model that we develop is consistent with what we're seeing with the samples that we'll draw in class. So we're going to check the theory against reality and see how close your sample means are from the truth. Okay, so X bar follows a normal distribution around the truth. This is from the central limit theorem. How do we use this? That's the main question, right? Like, we have a normal distribution. How do we use the fact that we know the sample mean approaches a normal distribution as the sample size gets larger? How do we use that fact? To do this, we're going to systematize how close X bar, the sample mean, is from the truth. So last time, just as a refresher here, we know the sample mean follows the normal distribution around the truth. And the distribution of the standard deviation of the normal distribution that the sample mean approaches, that is what we call the standard error. This is the variability in the distribution of sample means. And it follows this thing. So this is the standard error, which is sigma, which is the standard deviation of the population. So this is the population parameter, like we've talked about, divided by the square root of n, which we talked about this. It looks a little bit weird. Why is there a square root? We're going to come back to the actual shape for this thing, but I just want to give you some intuition for what this is doing. As you'll remember, as the sample size grows, the variability in the sample mean gets smaller and smaller. So I'm going to show you some pictures, but this is one of the things we found from last time. And you can see that in the notebook. I won't bring it up again, but you'll see it in the notebook. Because there's an n in the denominator, this thing gets smaller and smaller as n gets larger, as the sample size gets larger. So that's the one of the main results here, is that the distribution of the normal distribution that the sample mean follows gets smaller and smaller, gets tighter and tighter around the truth. And this is just a picture of this. So the example we're going to be using today is with wait times. So we have an average wait time of 12, and then a standard deviation of 2.5. And these are all in minutes. So my question to you, if I were to increase this to 200, this is maybe a warm-up question. Tell someone next to you what's going to happen to this distribution as the wait times go from, the sample size goes from 30 up to 200. So instead of observing the variability in averages over 30 observations, what happens to the distribution as we go to 200? What will this look like when the sample mean is over 200 observations? Take 30 seconds here, sketch out an idea, tell your neighbor something fun you did this weekend, and then tell them what's going to happen to this thing as we increase the sample size. Okay, anyone do anything fun this weekend? This past weekend? No, college is not for fun. Never do anything fun in college. I've gone back and watched like some of the classroom recordings, and whenever I make jokes like that, it never like comes across in the video because no one can see you laughing at my stupid humor. What's going to happen to the distribution of the sample means when the sample size grows to 200? What's that picture going to look like? Yeah. Get more narrow. So let's just plot this. So the sample size, which is larger, now has a tighter distribution. Someone explain to me why this is happening. Like, what's the intuition for what's going on here? This is a very well-established result. We've simulated it so many times. From last time, what's the intuition here? Why is it tighter?
The more samples you get, the larger the smaller the distribution.
Yeah. So as the sample size gets larger, it's harder to get the extreme values. Yeah. So we rolled a bunch of dice last time to get a 1 as our average of 2 dice. It can happen sometimes. But to get, and the way it would happen is you roll 2 dice, and they both end up as 1. But if you're rolling 200 dice, the only way to get an average of 1, an extreme value, when you roll 200 dice, is that all 200 of the dice are 1. And that doesn't happen very often. That's like 1 in 1 over 6 to the 200th power. That's a very unlikely event. So extreme values become increasingly unlikely when the sample size gets larger. So we get this tighter and tighter distribution. Okay, so that's kind of the intuition. And for the purposes of this class, the intuition is really all you need to know. I wanted to show you some of the math behind why this is true. A lot of you will have some interest in studying more of the rigorous side of this, like the math for how we know these things, beyond the simulations. Like, we're simulating these things, but you can do it mathematically. So the idea here is with n independent observations, and each time we draw an independent observation, there's variance of sigma squared. It's just the standard deviation squared is the definition of the variance. And then the sum of n observations has a variance of n times, the variance of n observations has a variance of n times sigma squared. This is just some of how many of you have seen this idea before? Yeah, some of you will have seen this in your stats class. This is just sort of how we calculate the variance of the sum of random variables. Just works like this. So if we're finding the variance of n observations of the same distribution, it's just n times sigma squared, which comes from this thing. And then to find the average, all we do is we divide the variance of the sum by n. So the variance of whatever a is divided by n is just the variance of a divided by n squared, which comes from the fact that we're squaring each of the differences between the observation and the mean. So then you can use these two facts together to get this thing, which is that the variability of the sample mean, which is the standard error, is sigma divided by the square root of n. This is not something we're going to be developing beyond this, but this is just sort of a more rigorous way of showing where the standard error comes from. It's like just when we take larger and larger samples, the possibility of extreme values goes down. Okay, so this is all, so far what we've done is that we've talked about distributions where we know the variability of the underlying population. Let me just pause here and sort of make this point a little bit more strongly. We don't observe the underlying population. I've said this in many ways, in many contexts. We do not observe the underlying population. We don't know its distribution. We don't know the probability distribution, which means we don't observe the true mean, right? That's the entire point of what we're trying to do here. So we don't observe the true mean of the underlying distribution. I can't see that the wait times for a given restaurant is 12 minutes. I can't see that. I also cannot see the variability in the distribution of the population. But for a second, we're going to assume that we do. So far, we've assumed that we know what sigma is. This is what allows us to calculate the standard error with the known population. So we're going to hold here for a second, and we're going to fix this problem later. We're going to make it so that we don't need to know the underlying variability in the population. But for now, we're going to assume that we do. Okay, so if we were to know not the mean, but if we knew the variability in the population, we can calculate everything just like we've done before. And the way we do this is with a large enough sample size, we can calculate the probability that X bar is, for example, within one standard error of the average, of the true average, of the true middle. Okay, so instead of telling you the answer here, we're actually going to spend a minute just thinking through how to do this. What's the probability that X bar is within one standard error of the truth? So we know what the distribution is that X bar follows. So we're essentially randomly drawing X bar from some distribution. And I'm interested in finding how close some random X bar is to 12, to the middle. So we're going to take, I want to push you here. I want to take a couple of minutes, and I want you to set up this problem. You don't need to solve it. No computation is required beyond some of the basic stuff. But I want you to set up how you would think about this problem. I want you to look to someone next to you, tell that person that you don't know how to do this yet, and then work through some of these things together. I want you to set up a picture first, and then we're going to do a lot of this on the board. Sound okay? Oh boy, that's not the enthusiasm I'm looking for. Let's see. Let me ask that question again. Does this sound okay? We're going to attempt to answer this problem, and then we will answer it together. What's the probability that I take a sample and the sample mean is within one standard error of the truth? The first thing to do, maybe calculate the standard error. What's the standard error with what we're given? And then draw a picture. Okay, take a couple minutes here. You will feel lost at the beginning, and then you will not feel lost by the end. Draw a picture. What's the someone help me out here. What's the distribution of x bar? Oh man. Someone help me out here. I'm looking for an answer. Someone tell me what x bar is. Is this too easy or too hard? Alexa, sis, I'm sorry. X bar is the sample mean. What's the distribution of x bar? What's the distribution of the sample mean? I see some people drawing things in the air. What's the name of it? Yeah, Ava. A normal distribution. If we know what sigma is, we know the distribution of x bar. Okay, so use this fact to then draw a picture of the probability that x bar is within one standard deviation of the truth. Has anyone done it yet? Okay, look around, see that no one else has done it, and then make an attempt. Maybe Ruby has. Okay. And then I'm going to ask one person to draw them on the board. Okay, does someone want to draw me a pretty picture on the board? Does someone want to tell me how to draw the pretty picture on the board? I know there's at least one right answer in the room. I've been watching. Yeah, Alexis.
So draw a horizontal line and then put x bar in the middle.
Okay, so something like this. Okay, so then say the next thing.
Put x bar like down there.
Down here?
Yes.
So we know this is a normal distribution, right? Our x bar follows a normal distribution. And like we talked about last time, the normal distribution is centered on mu with a standard deviation with the standard error, which is sigma divided by the square root of n. We eventually will center a normal distribution on x bar, but in this case, we know that this distribution, the distribution of x bar, is centered on the truth, not x bar. But it's a similar idea to where we're going. Okay, so Alexis has set up the distribution of x bar. Someone want to add to this idea? I think Alexis has the answer, but someone else want to help? How many of you have an answer? I will not call on you. Okay, Like 3 people. Okay. So what do we do when we're thinking about the probability of being less than something? How do we visualize that? So let's say we want to find the probability of being below A. How do we find that probability? Yeah, Ruby?
Would it be the area under
Yeah, so the probability of being less than A is just the area under the curve less than A, which, like we talked about last time, or 2 classes ago, is the CDF, the cumulative density function of the distribution. Okay, and then how do we find the probability of being less than B? Someone else. So just like with the last one, yeah, Kurt.
I mean, you could do it that way, just the area under B, or like the area above it, like -1, I think.
Okay, so we could do the area below B, so the area under the curve less than B, which would be the CDF of B. Or we could find the area above B and then subtract 1 from that, or subtract that from 1. Yeah, so either way we could do it using CDFs. Yeah, so we did a couple of these kinds of examples the last 2 classes. Okay, so with this as the cue, how do we find the probability of being no further away than 1 standard error? Yeah.
Do the CDF B as the CDF of A.
Okay, so we're going to look at and try to calculate the area that's within 1 standard error of the truth. And then to find this, we use the CDF of B minus the CDF of A. We're saying we want to find everything under B, and then we're going to subtract off everything under A. And that leaves us with the area between A and B under the curve, which is the probability of being no further away from the mean than 1 standard error. Okay, any questions here? I think there are a lot of questions, it seems. How many of you, does this feel generally familiar? You will have seen this in your stats class. Okay, so maybe we need some more work on this. Should we do another example? Okay, so the picture I want you to hold in your head looks like this. So we have wait times. The distribution of x bar follows a normal distribution centered on the truth with a standard error of sigma, which is 2.5, divided by the square root of 30, the square root of n. And the way we would write this probability is by finding the probability of being greater than mu minus 1 standard error, being above A and below B. So B in this case is mu plus 1 standard error. So it's the area between these 2 lines under the curve, which in this case, this is a general result that the probability of being between within 1 standard error of the middle, that's roughly 68%. It's not exactly 68, but it's roughly. Okay. So what we say is that following this procedure of randomly drawing a sample mean, roughly 68% of the time, it's going to fall within one standard deviation. Standard error of the truth. Our sample mean will fall within one standard error of the truth, roughly 68% of the time. Sometimes we say this is like a 68% confidence interval. That's how we define this thing, which tells us following this procedure, we're going to be within one standard error, roughly 68% of the time. Okay, should we do this again? All right, so my question for you, I want you to set up a visualization of the answer to this problem. We know what sigma is. And I'm giving you what the truth is, even though we're not actually observing this. We're saying, if we randomly draw a sample, what's the probability that we're going to be within two standard standard errors of the truth? So maybe set up what's the distribution of x bar, which we've talked a bit about here. But set it up as an answer to this problem and be as precise as you can. Maybe check with someone next to you as you're working through these problems. This is very similar, just a slightly different bound. Take a couple minutes here. Okay, someone want to help me out here? What's the probability? How would we draw the probability of being the sample mean being less than two standard errors away from the truth? Or yeah.
Just the same thing as before, but adding one standard deviation.
Okay, so instead of just looking at one standard error away, we're going to look at a second one. So in addition to the first, we just have a second standard error. So it gives us sort of more area under the curve. So this is mu plus 2 times sigma. And then this one would be mu minus 2 times sigma. So we're like 2 standard errors away on both sides. And then all we would do is then use this with our formula here. So it's just, we're looking at everything below this and above this. Okay, so then we just use the CDF of 2 standard deviations above minus the CDF of 2 standard deviations below. So this is the picture, which you've all worked with before, but let's actually calculate this number. So in the last example, I gave you the picture and the numbers here. I used Python to calculate these numbers. So I'm going to show you how to conceptualize calculating these probabilities. You can do this with that Z table in the back of your stats textbook. Z-scores allow us to do these things. but we don't need to mess with that stuff. You all ready for an exercise? I feel like maybe making this a little bit more practical might be somewhat helpful. Okay, so what we're gonna do, I don't sense enthusiasm. Y'all hanging in there? Okay, maybe writing this out in a notebook will be helpful. So I've made a nice little notebook for us. So all we're going to do with this exercise is just walk through calculating the probability of being close. So how close is our sample mean on average to the truth? So like we talked about in the slides here, we have a sigma of 2.5 and an average of 12. So all we're going to do is just write these things in our notebook. So we have mu is equal to 12. We have sigma is equal to 2.5. And then let's say our n is equal to 30. So this is the data we're working with. And then someone help me out here. How would we calculate the standard error? Standard error is equal to what? Yeah, Jay. The square root of n. Yep. So we have sigma, which is our 2.5, over the square root of n. So this is numpy. It's the numbers package. And then this is the square root function. So this thing will just give us the standard error. So you can see with this sample size, we have a standard error of roughly 4.5. If we were to increase the sample size to 300, for example, our standard error would go down. But let's keep the standard error at 30. So here we have a standard error. The next thing we want is to calculate, let's first start by calculating the probability that we're below 2 standard deviations above. So we want to calculate the probability of being on this side. So we want to be below mu plus 2 standard deviations. So let's start here. So let's try to calculate an actual number. We've been working with these things in code. So you all are familiar with the stats package, which I guess is not loaded in the notebook here. Let's from scipy import stats. And then we can use the stats package, stats.norm.cdf. So you're going to fill in some number here, which will give you the probability of being less than 2 standard errors above the mean. So it'll take about a minute here. Write something down, and then check with your neighbor about this. Check whether your number is the same as your neighbor's. Okay, someone want to direct me something to write into this into this entry here. What are we putting into the CDF? Y'all leave me on red. Yeah. So we have 12, which is our the population mean. If we run this, we get 1/2. So it's going to be exactly 1/2. This is telling us the probability of being less than the middle of the distribution. So it's everything below the mean, which is exactly 1/2, which is not quite what we want. Is it Chase? Alex. Have I called you Chase before?
Yeah.
Okay. So someone, 10 lecture points to Alex. Someone improve on this answer. It's not 12, but it's 12 is involved. Yeah, Chase.
Jeez.
Oh my goodness. Maybe I should be collecting lecture points. Jason, yeah.
12.5.
So why would it be 12.5? So I'm going to hand out 10 more lecture points. Everyone's getting lecture points, including me, apparently. Someone follow up on Jason. Yeah. 12 plus 2 times SE. No lecture points, unfortunately. What we're doing here is we're looking at 12. We're trying to find on the horizontal axis, what point should we be calculating the area below? What we want is the population mean, which is 12. And then we want to find 2 more standard errors above that. So that becomes 2. So it's 12 plus 2 times the standard error. You could use 12 here. You could also use just mu, because that's the variable for the average. So when I run this, I get a number. I'm going to write item at the end, just so we get the number itself. How many of you got 0.97? Okay, nice. So I'm going to test you again. So let's do another one. What's the probability? The probability of being less than 2 standard errors below the population mean. If you were to write this this line of code out in your notebook, Gemini will probably give you an answer. Try to write this out for yourself. Don't rely on AI to help you out with this one. I want you to actually check yourself. How would we go about computing the probability of being less than 2 standard errors below the mean? So it's, what's the probability that we're below this point? We're in the lower tail. How do we find that probability using a CDF? Take about 30 seconds here. Okay, someone help me out here. What are we writing? Ruby. Nice. Yeah, so then we use the location, which is mu, and then the variability in the normal distribution, which in our case is the standard error. So I write this out and I run this. Okay. How many of you got this number? And how many of you use this process, more importantly? Okay. So this is the probability of being 2 standard errors away on the lower side. Now, to find the probability of being in between these 2 values, all we have to do is find the probability of being below minus the probability of being below this value. So I want you to calculate the probability of being no further away than 2 standard errors from the average, from the population mean. The probability of being within 2 standard errors of the population mean. Take about 30 seconds here. I'm going to call in someone for their answer, and then I'm going to ask for a number. Like first off the process, and then the number. Okay, someone tell me your process. Yeah.
Copy the thing from about this. Yeah, that one.
Okay.
And then minus the second one.
Minus the second one. Okay. So we're essentially just following the procedure that we've drawn on the board. I say this in my intro micro classes, like when I'm doing microeconomics, I don't do microeconomics without a picture. I also don't do probabilities in general, especially in this way, without drawing a picture. On the mini exam, I will be asking you for pictures, so get in the habit of drawing the picture. We use it as a model because it's useful. So think about it in this way. We've calculated both of these things, and all we have to do is subtract the difference. So if I run this, I get this thing. How many of you got this number? Does someone want to interpret what this number represents? What is this telling us? Someone other than Ruby and Alexis. Yeah.
It's like 95% confidence interval, so 95% there's 95% those two deviations.
Yeah. So Jason is saying roughly, it's not exactly 95, but we approximate it within we call this a 95% confidence interval. 95% of our samples will fall within 2 standard errors of the mean. So when we draw our data over and over again, 95% of the time, roughly, will fall within 2 standard deviations of the truth. So what we're going to do next is actually simulate this. I'm going to have you draw a sample, and then we're going to check how many people in this room drew a sample that's within some confidence interval. This is how we define confidence intervals. Let me just jump back over to the slides just so we can write this out. So this is our confidence interval. What's the probability that the sample is closer than 2 standard errors of the truth? And this is the code that we just wrote out. Okay, so we're gonna actually generate some data. You're going to check whether your data is within 2 standard errors of the truth. We know what the truth is. We're going to pretend that we don't, and then we're going to check how many of you have drawn a sample that's close to the truth. Okay, y'all ready for this? We made a prediction. We used theory, the theory of the central limit theorem, to show us that the distribution of the sample mean it approximates a normal distribution, as long as we know sigma. This is the theory, and we're going to put all of our chips in. It's like we're going to make a big bet that when we run this a bunch of times, each one of you will run this separately on your computer. Each one of you will get a different number. There's enough of us that we're going to generate some data. You're going to tell me yes or no whether your sample fell within the confidence interval. We're going to repeatedly draw, and then we're going to put the central limit theorem on the line. And then we'll talk about it. Y'all ready for this? That's not the rousing enthusiasm I'm looking for. Okay, so I've written some code here. I'm gonna, instead of looking at 2 standard deviations, I'm gonna change this to being 1. So this is what's the probability of being within 2, just for sample reasons. Let's say 1 standard error. So all we have to do is take off 2 and 2. So it's just probability of being within 1 standard error. Now, what I want you to do is calculate the sample mean. So this is the sample. So we're going to run, each of you will run your sample. And then you're going to give me the sample mean. So your number will be different. You're going to write out the average of your sample. The sample here is just this thing. I want the sample mean. So you can write out sample.mean, which will give you the sample mean. And you can use item if you like. Just look like something like this. Okay, so we're going to find the 2 bounds. So I'm going to use ppf to find the upper bound. And then we'll use and then I'll find the lower bound, and then you'll tell me whether your value is within those 2 values. So here I want, I'm sorry. Let me just write this code out. This is calculating the 2 probabilities, and then I'm going to put those 2 probabilities into the ppf. So stats. You don't need to follow this. This is just for our purposes. Stats.norm.ppf, and then we're going to put 84. Actually, let's use 90. And then, so this is our upper bound. So we want the upper, and then we'll find the lower. So 90% of our data should fall within these 2 numbers, 12.75 and 11.25 roughly. So I'm going to go around the room. We're going to collect some data, and you're going to tell me your number, whether your number falls within this interval. So just check your sample mean. So for me, because this is less than my upper bound, than the upper bound I have here, I'm checking that this is below and it's also above. So my sample falls within the sample mean. Sorry, the 90% confidence interval. Okay, and what we should find is that 90% of the class falls within this confidence interval. We've made a sample, we've constructed the sample mean. If the central limit theorem is true, then 90% of your answers should be true. Okay, so we're going to construct a data set within 90 CI. And you're going to tell me yes or no. Ready? Should we start on this side? Everyone has a sample and ready to go? No? Okay. So if you don't have your sample and your sample mean, all you need to do is construct the sample using the code I've given you, and then you find the sample mean, and then you tell me whether it falls within the 95% confidence interval. Sorry, the 90% confidence interval. 90% confidence interval. Okay. So let's see. Anyone ready on this side? Okay. Yes. So if you're a yes, I'm going to write you as 1. And then if you're no, I'm going to write you as 0. Okay?
Yes.
Yes. Yes. Yes. Yes.
Yes.
Yes. Okay. Okay. What's your number? We can go back.
Yeah, we come back to
Yeah. Yes. 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 Okay, so this is unusual. We should have 90% falling within this interval, and it turns out 100% does. This is higher than we would expect. But this is one of the lessons here. That just simply by chance, drawing a bunch of samples, we have we don't have a lot of data in the tails. Any questions? So just by probability, we have most of the data in the middle. Where even though there's 10% chance that we should have something in the tails, we don't have.
He read it wrong. His is above.
Mine is above.
Yours is above. Okay, so we have 1, 0. So we'll switch this to 0. So it's not 100%. Okay. Anyone else make this mistake? We should have a few at least that are outside. So not between these two numbers. Okay, if we were to run this a bunch of times, we would get different numbers. Each of you, if you run it again, you'll get a different number. And sometimes that number will fall outside of this interval. So for example, mine, if I were to run this a bunch of times, I will get different sample means. And if I run this enough, I will end up with a value that's outside. Oh, that last one. It was 11.08. The last one was 11.08. And that was outside of this interval. It was below the lower bound. So a couple of results here. First, sometimes we can have all of the data in the middle, within our 90% confidence interval. Even though, on average, only 90% of the data should fall within that interval. The second result is that sometimes, even though we're very confident that our sample means will be very close to the truth, will be within that 90% confidence interval, even though we're very confident about that, sometimes we'll be outside of that interval. So even though we're saying most of the data is in the middle, we're still saying that there's some level of uncertainty, that we could be wrong some of the time. A 95% confidence interval does not tell us that that we're right. It tells us that we're right on average, and we're right, in this case, 90% of the time. But my sample, let's just see what the average is. So I'm going to find the mean of this thing, mp.mean. So even though we've constructed a 90% confidence interval, we have 5% of the data in both tails. So there's a 5% chance that the data will be outside, it'll be below the lower bound, and 5% chance that it'll be above the upper bound. Even in that case, just with the sample that we've drawn, more of it than we would expect falls within the middle, within that 90% confidence interval. But we could run this a bunch of times, and we would end up right around 90. Okay, do you feel this? Do you feel that your draw is just one? We're not making a claim about we're not making a claim with certainty. We're saying there's a chance that we could be wrong. There's a chance that a random draw could fall outside of our 90% confidence interval. So we can be wrong. We can be wrong that our sample mean is not that close to the truth. It's just on average, when we construct our confidence interval in this way, we will be close. Okay, questions about this? This is how we interpret a confidence interval. It's not making a claim about anything with certainty. It's making a claim about a probability. Yeah, Savi?
I just wanted to see the code that you used for the lower bound.
Yeah, so it's just the 5th percentile.
Oh, because I got a different lower bound. No, not that.
Okay, yeah, we can chat about that after class. Okay, this is a powerful idea. I think when we talk about confidence intervals, it's not always clear what we're talking about. We're saying if we draw a sample, 95% of the time it will fall within that, or 90% of the time in our case, it'll fall within that interval. In this case, we drew a bunch of samples, and 97% of them fell within the confidence interval, which is a little higher than we would expect. Often when we talk about like a 95% confidence interval, for example, we say we're 95% confident that the truth is in this interval. Although this is a bit of we're going to come back to how this is, there's some nuance to the way we make these claims. But this is how we think about confidence intervals. Okay, so this is all with when we know what sigma is. But like I mentioned at the beginning of class, in general, we do not observe the population, which means we do not know what sigma is. We've gone through this whole process of thinking about what happens when we don't know the underlying distribution. But everything up until now, we've assumed that we knew the standard deviation of the population. Anyone know what we do? How do we fix this problem? What happens if we don't know sigma? Yeah. So we're going to use the standard deviation of the sample standard deviation S, which we're then going to use to construct the sample standard error. Yeah. Remind me of your name? Luke. So Luke is saying, let's use what we can observe, which is S. We don't observe sigma. Let's look at S. So in the last 5 minutes of class here, I just want to show you some stuff. We're going to come back to this next class. The distribution of our sample standard error, just like what happens when we think about the distribution of our sample mean around the truth, the central limit theorem kicks in here too. Every time we draw a sample, we get a different variability in our sample. The sample standard deviation, S, has variability in itself. The variability of the variability in our data has some movement. There's variability in the variability of our data. This is just a distribution. I drew a bunch of samples and I plotted each one's standard deviation, S. and it looks like this. So there's variability in the sample, in the sample's variability. The truth is here. So S itself has a distribution. And it's, again, by the central limit theorem, centered on the true standard deviation. So S, the distribution of S, is centered on sigma. This is something we can use. So I'm not going to walk through the math of how we do this, but the extra uncertainty that comes from using S instead of sigma, so we just swap in S in place of sigma when we don't observe the population standard deviation. There's extra variability there. So we're not going to walk through the math there, but this adds some extra uncertainty. So if we use a normal distribution, we end up being too confident because there's extra variability in S around sigma. Okay, so S is random. Using it instead of sigma introduces a second random variable. And because of that, we have less confidence, less of our data is centered in the middle. So you've all seen a t-distribution before. This is the idea with a t-distribution. If we don't know mu, we use a normal distribution. The sample mean follows a normal distribution around the truth. But that's only if we know what sigma is. If we don't know sigma, we can approximate the distribution using a t-distribution, which captures the extra uncertainty that comes from using S instead of sigma. That's all we sort of have to know. There's a bunch of math behind the scenes. It's like the square root of a ratio of random variables. If you know anything about a chi-square, there's a chi-square in here. But the main idea here is that the t-distribution is more spread out than the normal distribution. And as the sample size grows larger, the variability in the sample standard deviation S gets closer and closer to the truth. This picture gets tighter and tighter around the true standard deviation, which means that the t-distribution gets closer and closer to the normal distribution. So as our sample size grows larger, we get closer and closer to a normal distribution. So a lot of times we approximate a t-distribution with a normal, but fundamentally the t-distribution is more spread out. So this is the foundation for the t-test. Essentially, the tails are heavier than the normal. Oh, I've gone over time. This is where we'll pick it up next time. This is the basic idea with how we think about how wrong we are with confidence intervals. And we're going to develop the t-test next class. I'll see you there.